Right, before we start looking at the Unit 4 kinetics, it's probably a wise move to discuss some of the stuff that we should know from Unit 2 from last year. So we'll start with this part on kinetics and collision theory. There's a few little bits and pieces that you need to be aware of here. First of all, collision theory is the idea that particles must collide in order for a reaction to happen, but it isn't just a collision that's important. The particles must have sufficient energy. In other words, they must have an energy, or they must collide with an energy that is above the activation energy. If they don't have the activation energy, then they'll basically just bounce off each other. For some reactions, particularly organic ones, the particles must also collide with the correct orientation, and that basically means that they need to be arranged at the right sort of angle when they hit each other to make sure that they react. And the reason why most collisions don't result in a chemical reaction is because they do not meet the second and third criteria. So they don't have enough energy when they collide, or they don't collide with the correct orientation. Right, activation energy, as you should remember from last year, is the minimum energy needed for a reaction to occur. On the screen now you can see the energy profile for an exothermic reaction. The reason why we know this is because the products, which are indicated in purple here, have a lower energy than the reactants, and that's indicating that the system, the reaction, has lost energy to the surroundings, which we would feel as heat. Right, very, very briefly, just talking you through this, you've got reactants, and then what we talk about in the middle is a transition state, and that's once you've supplied your activation energy, you get that state. So you've put energy in, and then energy is released when the products form. And without that initial activation energy, the reaction is not going to happen. So basically, you would not turn reactant to product. And that's known as our activation energy. Right, this is quite important because lots of people get confused with this, and in the examiner likes to ask the question, why does the reaction slow down over time? And the most common wrong answer that a student will give in this scenario is that they'll say the reaction runs out of energy. And in reality, it doesn't run out of energy. What happens, as you can see on this diagram here, is blue is colliding with red in order to make purple. And as time progresses, the blue and red particles get used up, these reactants run out. So eventually, when you get to near the end, there are very, very few particles left. And then once you reach 100%, as you can see over here, there are no red and blue particles left. Therefore, the reaction stopped. Right, so talking about what speeds up the rate of a chemical reaction now. Basically, there are four factors that you need to know. Surface area, pressure, concentration, and then, of course, you've got temperature and a catalyst, but we'll discuss those separately. In this case, we're looking at surface area. So as you can see on the right-hand side of the screen, you've got three different sort of arrangements. Powder at the bottom, big chunks at the top. Now, the key thing to note here is that only the particles on the surface of a solid can react. So when you look at a big chunk, all of the inside is unobtainable and cannot be sort of reacted until the outside layer has worn away, or reacted away if you like. So the key phrase here is if you increase the surface area, and it's important that we sort of emphasise the red text here, there'll be more collisions with an energy above EA, so the rate of the reaction will increase. And it's very easy to increase the surface area of a solid. You just compress it down until it forms a powder, and a powder will react very, very quickly, whereas these solid chunks will take a long time to react. And in this particular case, this reaction here, you've got calcium carbonate and acid reacting, and you'd probably realise that if you carried it out with powdered calcium carbonate, it would be quicker than if you carried it out with calcium carbonate chunks. The key point here is, provided you use the same mass of calcium carbonate in both reactions, you will still get the same amount or mass of products formed. The only difference being that in the powdered reaction, the products would be formed at a faster rate, but you wouldn't actually get any more product formed. Right, okay, so very quickly looking at the effect of surface area on rate of reaction, you can see two examples here in red and green, and then the third one in blue, which is basically powdered solid. And what you're seeing, again, by all of the lines reaching the same point, the same amount or the same volume of gas is being evolved, but in the blue scenario, that amount of gas is being evolved quicker than it has in the green and in turn in the red. So essentially you've got the same amount of product, but it's just being obtained faster or at a higher rate with the powdered marble or calcium carbonate. Right, okay, concentration is the next thing we need to look at, and this can cause, again, quite a lot of confusion. If you look on the left hand side, there's a low concentration of red and blue particles there, and then on the right hand side we've got a higher concentration. The concentration is the number of particles per unit volume. So as you can see on the right hand side, we expect there to be more collisions, and if you look very carefully you can see on the right hand side the particles are colliding more frequently. All the particles are all moving at the same speed because the temperature in both of these samples is the same. But the reason why we've had more purples produced on the right hand side is because the concentration of reactant is far greater on the right hand side, therefore we've ended up with a higher rate of reaction. There's been more collisions, essentially giving us a higher rate of reaction. Now we could leave that for a while. One of the things that this does illustrate, if you look on this side, is that we could probably leave that for a few more minutes, and there might be a scenario by which the red and the blue that are left over don't actually collide at all. And that's why when you've got some reactions, you start off and you think, right, we've got 1 mole of solid, we should get 1 mole of product. In reality, sometimes you don't get that because not all of your reactant will react. The reactions don't always go to completion because reactants remain unreacted, basically. And this is only a small scale diagram with, you know, a handful of particles. If you imagine that there's moles and moles of particles involved in chemical reactions, then you can start to see that if you've got millions upon millions of particles, then surely 1 or 2 are, you know, maybe might not going to react because they might not bump into each other because the product essentially gets in the way. Right, so looking at concentration here, we've got 2 lines again in red and green, and then the blue line indicates the higher concentration. How do I know this? Well, if we look, we can see that the blue line is achieving the same volume, but we've got it quicker because the concentration is higher. So what we're getting at is that as you increase concentration, the rate of reaction will increase. Right, the next one is pressure, and this really only applies to gases. If you increase the pressure, basically that's the same as decreasing the volume. So if you look on the right hand side, we've got a far higher pressure because we've got a smaller volume. So we're going to get more collisions, and we'll watch this run through, and you can see again that the particles are colliding more frequently on the right hand side because there's a greater pressure. You're bringing them particles closer together. There are more collisions with energy above EA, therefore a greater rate. The one on the right hand side is already finished now. Now again, we could leave the left hand side one to go on a little bit longer, and it might not all react, but the point of the animation is to show you that the increased pressure has contributed to a greater rate of chemical reaction. And again, if we look here, another 3 examples, different pressures, 100 atmospheres, 200 atmospheres, 300 atmospheres, and the 300 atmospheres pressure is by far the quickest again because the particles are again colliding more frequently and there are more collisions with an energy above EA. Right, the last thing we need to look at is the temperature. Now, temperature is a real tricky one because it's by far and away the most efficient way to increase the rate of a chemical reaction. When you increase temperature, the particles on this particular animation, if I just cool it down first of all, the particles move very slowly when the temperature is low. As you increase the temperature, what you do is you give the particles more energy. This means that they collide more often, that's the first very important point, and they also collide with more force. And those two factors mean that there are more collisions with an energy above EA as you increase the temperature. And when you're answering this in an exam, it's very important that you mention that not only are there more collisions, the collisions are also occurring with much more force or vigour. And therefore that twofold effect leads to an increase in rate. If we just take the temperature to the top, you can see that the particles are just moving around like crazy, and the collisions that are happening are absolutely far, far greater than they were in the first example where the particles had a low temperature. But not only that, you can see that every collision is colliding with more force, and that is a big factor as well. Right, okay. So, just a reminder, at higher temperatures the particles are moving faster, they collide more frequently, and they also collide with more force, so there are more collisions above EA, with an energy above EA. And just looking at this, we've got a couple of examples to show you here. Again, the three scenarios that you've got, and these again are different temperatures, 300, 325 Kelvin, 350. Now as a general rule, if you take the temperature up by 10 degrees Celsius or 10 Kelvin, then you would approximately double the rate. Now that depends on the type of reaction that you're dealing with, but it's a rough guide to use. And if you were going to change one thing to increase the rate of a chemical reaction, then temperature would be the one that you would increase, because that has the most dramatic effect on the rate. Right, now that's everything that you'd expect to know from the first part of AS. The next part is to start looking at Boltzmann distribution curves.